Okay, welcome everyone. I'm Aleksander Mądry. I'm a professor at MIT, but also a faculty lead on the CCL MSR Trustworthy and Robust AI collaboration. So we have an interesting event ahead of us today, but to get us started, I will hand off to Eric, who is the director of this collaboration.
Well, thanks, Alex, and it's great to be here with everybody. It's been a joy to work with Daniela, Alex, Evelyne, who you'll hear from tomorrow and later today, and so many of you collaborating professors and researchers and students as we conceived and brought up this MIT Microsoft Trustworthy and Robust AI collaboration that we finally called TRAC. Many of the concerns with AI in the open world, I think, can be summarized as being concerns about building trustworthy AI systems that align with the intentions of the designers of the systems. But I would say that more generally align with human intentions and values. We seek robustness to assure good behavior when these systems are thrown into the unmodeled complexities of the open world so they can perform well. We want to minimize inadvertent effects. We want to ward off manipulation and disruption by malevolent actors. And this whole endeavor includes developing and refining methods that can enable engineers as well as end users to interpret key aspects of the rationale for recommendations and actions, to understand and address weaknesses and failures. Other directions include developing principles and practices that enable us to reuse models in new contexts and domains, where we can't assume that we have the same distributional alignment with training and validation and test data. Anyway, it's been inspirational to see progress on the collaboration over the last year on the funded projects and collaborations in topics we'll hear about today and tomorrow, and robust machine learning, safety in AI systems, fairness, interpretability. So I'm looking forward to the workshop, kicking it off now, and to a great lineup of talks coming up. Let me now turn things over to Daniela.
Hello, everyone. I am so happy to be part of this meeting and this effort, together with Eric and Aleksander and all the super talented researchers. And Eric summarized the objectives of our project very well. The whole thing started about 2 years ago, and I think ours was among the first research activities to highlight the importance of trustworthy AI. In the meantime, over the past 2 years, the number of papers that are addressing issues foundational to this field has gone up. The National Science Foundation has started a program with institutes devoted to studying this issue. So altogether, I would say that we are part of a very exciting and important ecosystem that will have tremendous impact on how the field develops. And with this, I am really looking forward to hearing the talks and to participating in the breakout sessions, and super excited about the program, about continuing to work with Eric, with Evelyne, with our colleagues from Microsoft, and continuing to keep this gradient of very positive contributions. So back to you, Aleksander.
Yes, thanks, Daniela. Thank Eric. Okay, so we can get started with the talks, and the first thing we will do is our first keynote talk. Our keynote speaker is Kostis Daskalakis, who is my awesome colleague at MIT. So Kostis did a number of things in his life, and he's still doing a number of things. So he has, of course, like breakthrough contribution in game theory. But what he's thinking quite a bit right now is about trying to, get a reliable inference from data, especially data that was censored or was in some other ways purposely biased. And essentially, this is like a really interesting work that I think is at the forefront of what AI in the wild is about. And I will just let Kostis to tell you more about this. Thank you. Kostis, you are on.
Thank you all so much for being here and the invitation to present. I hope you can see my screen. If not, let me know. So first of all, it's a big pleasure because I do think that this is a very important area. Oh, you cannot see my screen. Well, that's bad. Let's try to correct that. Let's see, we did try that. All right. Okay, so I hope you can see it now.
We can.
Cool. So yeah, so it's a super important area, and the Microsoft and MIT collaboration is really at the forefront of what is important to figure out for the reliable applications of machine learning and statistics in the wild world. And today I'm only going to talk about one aspect of how to make statistics and machine learning reliable, looking at the foundations of statistics. But of course, the question is much, much broader. So I'm going to talk about robust learning from sensor data. And I will let you figure out by yourselves how this fresco from the Minoan Palace is relevant to that question. So before I begin, and I will come back to this problem later, let me give you an amuse bush that will actually convey some of the motivation and later on some of the ideas of what goes into building robust statistics from sensor data. So in this figure on the left, I'm showing you two probability distributions. One is supported on 0, 1, and the other one, so F is supported on 0, 1, and G is the conditional distribution of F in the interval 0 to 1/2. So in particular, F, so the log density of F is a sinusoid, and G is its conditional distribution in that first half of the interval. And I want to do this little experiment. So I want to take a large sample S from the conditional distribution. So I'm going to see a bunch of samples falling in the interval 0 to 1/2. And what I'm going to do is I'm going to try to fit the best distribution I can that has a log density, which is a polynomial, right? So this integral you see here at the bottom is just the normalization factor. So what I want to do is I want to fit the best distribution that has a log density that's a polynomial to samples that I got from this orange distribution. And the question I want to ask is, after I do that, how well would the fitted density extrapolate? So how well would it do if I change the normalization constant to the integral over the whole interval of this same log density? How well would it do in the part of the domain that I have not observed? Okay, so that's sort of like a metaphor of what happens when you censor data from a distribution. So you see only data that fall in some domain, subdomain, and you want to learn something that you then want to apply to the full domain. And let me show you what happens. So something very interesting happens. So in this picture here, you see how the approximation behaves after you extrapolate, depending on what degree you use for the polynomial Q. So the blue line is the original density, this density F. And depending on what degree you choose, you see what extrapolating distribution you get. And what is pretty interesting about this is that you get this non-monotone behavior. So degree 10 gives you something decent. Degree 12 gives you something horrible. So this is the distribution you get from degree 12 if you extrapolate. And then from degree 13 and onwards, you get better and better behavior. At degree 15, you're doing a pretty good approximation once you extrapolate. So you get this weird non-monotone behavior. In fact, you have this double descent behavior. So small degrees are descent, then this 12 degrees horrible, and then it starts getting better, and then it becomes better and better and better and thereafter. So what happens here, and that conveys some of the intuition and the motivation, you get overfitting. So by looking at only a subdomain and trying your best, the best you can to fit a model there, you're overfitting in the rest of the domain. So you should be careful when you do that, when you focus on only a subdomain and fit your model there and then use that to extrapolate. So that's sort of like a little motivation for the talk, but the executive summary is the following, that very often when we collect data, there is some systematic selection bias in how we collect the data. And if we're naive about it, that can lead to prediction bias if we trust our models too much outside of the domain of the original data. So the goals of this line of work that I'm about to present is to decrease this bias by developing statistical methods that are robust to what are called censored and truncated samples. So these two definitions, so the definitions of censoring and truncation are given here. So truncation refers to the phenomenon wherein samples that fall outside of some observation window are hidden from observation, and their count, their existence is also hidden. Censoring is the same, except it's a bit easier. You at least get the count of how many samples were censored. Of course, censoring and truncation appears a lot in science, and it has to do with the fact that, you know, measurement devices have limitations and they get saturated outside of certain bands, so the readings might be unreliable. But also it comes because of limitation in data collection, and this could come because, you know, you design your experiment incorrectly and you didn't collect all the data you should be collecting, or because of legal or other considerations that may disallow you from using some of the data that you have collected. So of course, these types of issues arise a lot in science, economics, social sciences, and clinical studies, and it's a well-studied topic in statistics and more recently in machine learning. So to motivate a little more with some examples, let me talk about some like real applications out there where truncation naturally arises. So my first example is actually sort of like a debate that was happening in the 50s and 60s in the social sciences around whether IQ contributes to the income of low-skilled workers. Okay, and of course, what is the definition? If we were going to talk about this mathematically, what is the definition of low-skilled workers? So the running definition for our purposes would be a worker who is paid under a certain threshold of dollars per hour. So say $10 per hour, or like I guess back then something smaller per hour. So a natural way to understand whether IQ contributes to the income of those low-skilled workers is to go out and collect data. And what these researchers did is to go to a neighborhood to collect survey data. So go to a neighborhood that is a poor neighborhood. So the selected neighborhoods that were where the household income was below 1.5 times the poverty line, and to collect data there, where for every individual, XI contains a bunch of covariates, including IQ, occupational training, education, etc. of that individual. And YI is the earnings of that individual. And then naturally, what you would like to do is to fit some model to relate X to Y. And after you fit that model, look at the coefficient of the sitting in front of the IQ covariate to understand how much it impacts the earnings of the individual. So the obvious worry you may have hearing about this setup is that there is some thresholding that happens because I decided to go and collect my data in a particular neighborhood whose income is below certain threshold. Okay. Of course, these are the relevant data. Where am I going to find low-skilled workers? Mostly in a poor neighborhood, but there is some thresholding that happens there when I choose to go there. And that thresholding introduces bias if I try to fit a model naively on the data that I collected, as was shown by Hasman and Wise in an impactful econometrica paper in the 70s, where they debunked prior work which had claimed that the effects of education are strong, but of IQ are not. And the mental picture that I would like you to have for what goes wrong here is the following, that when I do linear regression, my mental picture of the world is that the data that are collected are explainable by a linear model, and in particular, you have data that are scattered symmetrically around the true line that you're trying to reconstruct. So yeah, so if you have data that conform to this nice mental picture, doing least squares regression is a good idea. But in the application that I just talked about, what happens is that you focus on a particular neighborhood, and by doing so, you are thresholding the y variable, the income, to lie below a certain threshold. So this line here is the income threshold for the neighborhood that you chose to do your survey on. And out of all the possible data that you see on the left that you could have collected, actually, what you go and collect are the data that are below the line. And for this data, this flashing line looks like a much better fit to explain the data. But that fit is biased. And the reason it's biased is because you did a bad data collection. So this is a mental picture that I want you to have for why truncating, doing supervised learning where you have truncated your data, in this case, you have truncated them as a function of the response variable, may lead you to a biased model if you are naive about fitting a model. So my second example, I want to go to a different application that is much talked about recently in machine learning, which pertains to what was discovered by Boulamini, Zebrou, and others about the failure of machine learning models to predict well in certain subpopulations. In this case, gender classifiers were not doing well on people of color. And of course, after this was pointed out, this were fixed, of course. But so the interpretation of what was going on here was that the training data that were collected for the purpose of building the classifier contain did not contain the right proportions. Let's say that the truthful proportions, the true proportions of different subpopulations, or enough individuals from certain subpopulations, and as a result, the training loss of the gender classifier that was built was not paying enough attention to certain subpopulations, with the inadvertent result of doing badly on those subpopulations. And that is an example where now I have a supervised learning application where there is bias that maybe depend on the label, maybe depends on the image itself, but in any event, being naive about fitting a model there leads to a biased model. So for my last example, I wanted to talk about an even older instance of bias in the sciences, and that's coming from astronomy. And that bias arises because light dims with distance, like 1/r squared, and as a result, brightness limited surveys of the sky do not select objects with the same brightness at different distances. And if you're naive about fitting models on the data that you collect this way, you get this false trend of increasing brightness of stars the further away you move from the Earth. Okay, so that's called Malmquist bias, and astronomers have been finding ways to correct for that bias for the past century. And that's an example of an unsupervised learning problem. So just to be precise about the model for trying to capture these types of situations, let's assume the following. I will first state it abstractly and then give a specific instantiation of it. So here's what happens when you're trying to do regression or classification, but you have truncated data. So you can think of your data, the training data, being produced by the following data factory. So in the beginning, you sample some covariate vector X from some distribution. Then what you do is you use a ground truth model plus noise that you sample from some noise distribution to map the covariate vector that you chose to some latent code Z. And then there is a little daemon that looks at X, the covariate vector, and the latent code, and with some probability decides to throw away that sample that was created. With the remaining probability, the sample is kept, and then the latent code is mapped to some label. And then that sample point you created containing the covariate vector and the label is added to the training set. Okay, so the goal, okay, so that captures truncation because at one step of the generation process, you throw away samples you should have kept. So the goal is to estimate the ground truth using a training set that was produced in the way that I just described. So does this capture, so this captures truncation, and let me try to instantiate this to give, for example, a model of truncated logistic regression for my example. As you say, phi, the truncating function, might be known because you know the behavior of your measuring devices, or you know, like the legal constraints that prevent you from using some data, or phi might be unknown, and maybe you're also interested in estimating that. And you know, in that case, you would probably be making some parametric assumption, but not necessarily to make the problem identifiable. So in any event, so let me show you how this model captures a logistic regression from truncated samples, just to put some more concreteness to this model. So to capture logistic regression, what I would do is I would, first of all, my ground truth model will be a linear model. So the covariate vector is mapped linearly to the latent code. And you know, like I will be adding logistic noise there because I'm shooting for logistic regression. So here's what happens. So after you sample your covariate, you center a logistic distribution around the projection of your covariate to the ground truth model, the coefficient vector. Then truncation happens. So in my setting here, you know, the very extreme parts of the distributions are truncated out. And for whatever survives, what happens in logistic regression is those that have a positive probit are mapped to label 1. Those that have a negative probit are mapped to label 0. So this is how you can use this model to capture logistic regression. In this case, you instantiate this model with a linear model, and you instantiate the projection with just, you know, like a step function at 0. That's just an example of what you can capture with the model. So similarly, you can define a truncated density estimation model where you sample a covariate vector of some family of distributions that you want to identify, and that sample is either thrown to the trash or added to your training set. And again, you want to estimate the distribution using truncated data, knowing phi or maybe not knowing phi, and making some assumptions about it. So this is sort of like to put some concrete model to the problem. So, but the question, the main scientific question is, how can you train an unbiased model, so a model that identifies the true, the ground truth, as opposed to some other biased model, when you have samples that are truncated in that way? So that has been studied a lot. Of course, there are many applications and many instantiations of that. So it has been studied a lot, starting from Bernoulli, who was, you know, trying to prove the effectiveness of vaccination, but also some of the founders of the fields of statistics and then econometrics. And of course, it's intimately related to the problem called domain adaptation in machine learning. So, and of course, what you would expect is the problem to be solved, but it is not solved. Interestingly, there are important technical challenges that still exist in the foundations of this field, and these challenges are motivated by dealing with high-dimensional data and computational efficiency that's associated with that. So the challenges in the existing work is that the statistical error rates that you get, while scaling nicely with the number of samples that you collect, they have an unclear and sometimes bad dependence on the dimension. how many parameters you're trying to identify in your ground truth model. And the algorithms are not efficient or provably converging. So in a line of work that I've been pursuing with various collaborators, we have been trying to change that and obtain computationally statistical efficient algorithms that can also handle arbitrary truncation sets. Many times in the literature, they consider very specific types of truncation. We want to handle arbitrary measurable truncation sets. For example, I don't see any reason why, for example, like the data that some legal constraints preclude you from using would be a convex set or anything like that in the domain where the data lies. So we have been able to get results from some of the basic statistical problems of truncated linear, logistic, and product regression, high dimensional regression, so that is compressed sensing, and also even non-parametric density estimation. And just to give you a sense of the types of results that we get is that, for example, like for linear regression, we get the rates that you get without truncation, which is root dimension over n. For compressed sensing, you get the rates that you would expect, which is the sparsity times log the dimension over the number of samples. And it's a widely open field right now, pretty exciting. But I should pause a little bit and ask why now? Why are we able to get these results now? And I would argue that the reason we can't do that now is because there is a confluence of ideas from different fields that allow us to make progress. So in the foundations of what happens in trying to build robust models from truncated data, you use concentration and anti-concentration of measure results that have been proven recently. On the algorithmic front, you use our great now understanding of the properties of stochastic gradient descent. And also, very importantly, when you take those theoretical results to the practice, building gradient descent-based algorithms around your models allows you to exploit the hardware and software optimization that we have for implementing gradient descent-based methods and tackling models that contain neural networks. I won't give you proofs of my but I want to give at least an impressionistic picture coming back to my amused bush of how we get those results. Remember, like when I was trying to fit a polynomial log density on this conditional distribution, I was having this overfitting issue where I was overfitting to the details of that conditional, and I was not extrapolating well. But eventually I could. So eventually, after I crossed the threshold for the degree of the log density I was fitting, I could extrapolate well. So I want to pose a philosophical question, which is, under what condition should you be able to extrapolate well? Okay. And here's a little theorem, like a little vignette. And that vignette is actually a corollary of anti-concentration of measure. So suppose, okay, so this is the theorem that sort of conveys some of the ideas. So suppose that P and Q are distributions in the hypercube, on the hypercube, whose log densities are polynomial of a certain degree, K. Now suppose that I don't have access to these distributions over the whole domain, but over some subset of the domain. But let's assume that this subset does not have trivial measure. It has some, like non-trivial measure alpha. Lebesgue measure alpha, because the whole hypercube has measure 1, volume 1. I want my subset to have some non-trivial measure alpha. Then here's a claim that if I compare the total variation distance of the distributions over the whole domain and the total variation distance of the two distributions conditional on this subset that I can observe, these variation distances are related to each other. How related they are depends on the dimension, the dimension D. Alpha, which is how much volume this set S has, and K, the degree of the polynomial. So the implication of this type of results is that if P and Q are far in the whole domain, but I only observe those distributions in a subset of the domain, they won't appear to be too close in that subset. In other words, if I'm fitting data in that having access to the conditionals, I'm not gonna believe that something is close to the target when the whole domain is like it's far. So if it's far in the whole domain, I will see some signature of that in conditional distributions over a subset of the domain that has some non-trivial measure. So this is sort of like an impressionistic picture and a theorem for why or when you would expect extrapolation to actually arise. This sort of like finishes my technical section, and just for fun, let me show you some applications of this work on some easy examples. So for my first example, I wanted to do some logistic and probability regression on synthetic data. So for my synthetic data, I'm going to choose a ground truth vector in 10 dimensions. I'm going to choose covariate vectors again in 10 dimensions. And I'm going to run either a probit or a logistic model. So I'm going to center a logistic or a Gaussian around the inner product of, like my ground truth coefficient vector with one of my samples. I'm going to add noise to that. So I'm going to center that distribution at the right point. I'm going to truncate at some half open interval, the latent code. And then I'm going to do projection as I usually do in logistic regression. So in particular, when my truncation is exactly at the origin 0, I will only be seeing positive examples. So the way I have set this up is a better truncated at some negative C. Otherwise, I would only be seeing positive examples. I would never be able to fit anything that's reasonable. So here on the right, I'm showing you what happens on the left if I do truncated probit or probit regression, naive probit regression on this data. On the right, I'm showing you logistic regression. Naive is the blue line, and the real one, the truncated one, the careful one with the red line. And as you see, even as the truncation parameter goes very, very close to 0, while the blue line, which will eventually be seeing only positive examples, does badly, the red line maintains its accuracy in this synthetic data. So and here probit does a bit better than logistic. So that's my synthetic example. So here's my real world example. So here I got data from the million song dataset. And here's my setup. So the covariate vectors now are going to be the song attributes. The latent code is going to be the year the song was recorded. And my truncation will be half again open interval. So I'm only going to be seeing songs recorded after a certain year, not all the songs recorded that I have in my data set. And the task is to predict whether a song was recorded before 96 or after 96. So in particular, again, here, when the truncation becomes 96, I only see positive examples. There's no way to learn, but hopefully I could do something, with truncation even up to 95. And here's what I get. So blue is naive logistic regression. Red is the R-truncated regression. Again, after 95, 95 is really like, I only see songs from year 95 and after, and I want to predict whether they were recorded from 96 and after. So again, of course, that's my worst performance. So here is when I have no truncation. So I get this 70% accuracy without truncation. With truncation all the way to year 95, I get, I don't know, 60 or something, and below that, and you see the comparison of the two lines. Of course, this is not a synthetic example. The data do not conform with logistic regression. Even with full data, it doesn't do great, but it maintains its reasonable performance even as you truncate the points. Okay, so my final example, I want to take it to the more ML world. So here, I'm giving you a metaphor for an extreme domain adaptation example. So here I have a data set that has, I don't know, a subset of cellulae that is balanced, male or female. On the left, you see a subset of the cellulae data set that is disproportionately more male than female, but also the images have been flipped. I want you to take this as a metaphor of settings where the support of the tested distribution is measure 0 on the support of the trained set distribution. So here, if you just train AlexNet naively, you get a 55% test accuracy. I don't even know how it gets it. Maybe something with the eyes, the colors of the individual. I don't know how it even gets 55%. But if you do more sophisticated methods, you can boost that higher to 80%. I mean, we didn't try too much, just for the purpose of this talk. In any event, so that brings me to the conclusion of my presentation. I hope I convinced you that, unless of course you probably already knew, that systematic missing of observation leads to prediction bias if I'm naive about it. That calls to lots of considerations about how you use those naively trained models. In our work, we focus on a particular aspect of that, which is, can we decrease bias by being a bit more sophisticated, taking into account the truncation that has happened? We propose a general framework based on gradient descent methods that applies to general, even neural network models. We instantiate that to get end-to-end guarantees for some open problems in statistics. And as I sort of like conveyed with my amuse-bouche example, we can even handle non-parametric problems. But as future work, I would like to see more work in that frontier of like pushing beyond. So these methods are MLE based. So we can do a lot of non-parametric stuff, but I would like to see a lot more push towards reducing the parametric assumptions we make and also applying them to practical settings. Thank you very much.
Thanks so much, Kostis. This was really, really awesome. So we have like 2 questions, but we don't have much time. So maybe like there will be just one quick question and the other quick question. So the one quick question is essentially like, is this extrapolation theorem you showed tight? Like, do you know whether these bounds are actually tight, or this is just what you could prove so far in terms of trade-offs?
It's not. So first of all, like the way I showed it, I simplified it a little bit. For example, the lower bound, the left-hand side I explicitly made it looser than the theorem in the paper. So the degrees are not actually k, but they're more like squared on the left-hand side. But yeah, I don't know if it's tight. I mean, we use Carberry Wright. We use a sequence of steps. I don't know that it is tight.
I see, great. And now the other question is, so one thing that you assume, and in some ways you need to assume it, is that the truncation mechanism is known to the to us. What if it's not the case? So imagine that I would give you 2 levers, and whenever I know that these levers correspond to very different truncation mechanisms, but I don't know what they are exactly. Like, would it be something I could use to try to at least diagnose that there is some bias, or that like my current model is not doing well at debiasing it?
Yeah, that's a great question, and that's certainly one of the lines of work we want to pursue on the more practical front. First of all, as you say, from a theory standpoint, there are theorems. For example, there is a theorem by my student Manolis Zabetakis in collaboration with Christos Jamos and his student Vasilis Kondonis, where they assume that they don't know the truncation set, and they learn both the distribution and the truncation set. There are some non-identifiability issues that may arise there, so you have to be careful about how you formulate your problem. But for a more practical standpoint, I think it would be a great, certainly empirical thing to try to get data sets and the published models that people publish based on those data sets, and try to do further truncation by yourself, apply these robust methods, and see how robust the models that they publish are to your further truncation, right? So if for example, you do the counter positive, right? You say, look, suppose what these guys publish, the data set they have is untruncated, and suppose they fitted a model well. If that's the case, then if I truncate even further and use these more sophisticated techniques, the model that they publish should be robust to my further truncation. If it fails to be so, then that's a sort of like a call for understanding, what went wrong in their data.
Okay, this is great. Thank you so much for this talk. Now we are kind of switching to the next segment, which are the short lightning talks. The important thing is that we need to switch way we connect. So essentially, there is now information that Jen just published that essentially you should follow. And I will see you there at the lightning talks just in a moment. Thanks.
Thank you very much.
Thank you again, Kostis.